In this video, we are going to examine the liquefaction process, the technology of the liquefaction process, and its thermodynamics. Liquefaction is a different process than condensation. Condensation is a process that we carry out at the vapor-liquid equilibrium domain. Liquefaction is the process we carry out where our gas cannot be condensed either by cooling at constant pressure or compressing at constant temperature. In other words, our fluid is above its critical temperature. So let's start looking at the critical temperature, the subcritical and supercritical temperatures, the isotherms, and how the fluids behave in those domains, and then the necessity for the liquefaction. So here we have a PV diagram of a fluid where we have vapor-liquid equilibrium. On this PV diagram, we have an isotherm that goes through the liquid to vapor transition and then is expanded further at constant temperature. When we take this fluid in the vapor domain, at this temperature, if we start increasing its pressure, when it arrives at the vapor two-phase coexistence envelope, the fluid is going to condense. It will start to condense, and it will continue to condense until 100% of it is liquid. If we continue to increase its pressure, and of course in this domain, between liquid and vapor coexistence domain, the increase in pressure doesn't happen. We have to remove the energy somehow because condensation is a constant pressure as well as a constant temperature process. After 100% of this fluid is in the liquid state, so-called 100% of course, further compression does not induce too much change in the volume. So we have an abrupt increase in pressure, but very small decrease in volume. So this is the behavior in the vapor-liquid coexistence domain under subcritical conditions. At the critical point, our fluid undergoes this saddle behavior. So this is the critical point. All right, let's label this as C. It goes through the saddle behavior. We examined this when we were learning an unideal fluid behavior and its equation of state. So, but still, beyond the point of critical point, beyond the critical point, we have a fairly uniform behavior. When we take a fluid that is far beyond the critical point, the temperatures are far higher than the critical temperatures. You see that taking this fluid at this constant temperature, let me call T hot, all right, at this hot temperature, compressing the fluid does not make any difference. In terms of phase change, it is still in the gas phase. So we have to make the distinction between the gas, liquid, and vapor. Liquid is the condensed state, that molecular interactions are very high. Vapor is in equilibrium with its liquid, but gas is totally independent. It doesn't have a liquid that it is in equilibrium with. How am I going to take that gas, which is above its critical temperature, under normal conditions, for example, at room temperature, and how can I liquefy it? Number one. Number two, why should I? All right, so the second question is, why should I liquefy this fluid? Now, the why question is answered because of the technological necessities. I will give you two examples. One of them is the liquefied natural gas. Liquefied natural gas is a common commodity that we purchase, we sell, we transport, especially through the sea transportation methods. But transporting natural gas, if you don't have a proper pipeline, is very expensive if you are going to transport it as a natural gas, because you need a huge volume. What is this volume? I will write it here, and this is just the rule of thumb. It is not 100% quantitative, but remembering this is going to help you when you are analyzing systems that involve liquids and vapors and gases. Now, the volume taken by a liquid is about 1,000 times smaller, all right, approximately 1,000 times smaller than its corresponding volume. And of course, this is the specific volume. All right, so in other words, rule of thumb, this is not an exact number, that if you take 1 cubic centimeter of water in the liquid phase, if you evaporate, you get 1 liter order of magnitude of its vapor. All right? So the ratio is 1 to 1,000. It's an order of magnitude. It's an order of magnitude. This is not an equality, but it's an order of magnitude comparison, that the volume of vapor is about 1,000 times greater than the volume of the liquid. In other words, if I liquefy natural gas, I can carry the same amount of natural gas in a vessel that is 1,000 times smaller when I attempt to transport it in its gas state. As a result, liquefaction has a transportation advantage in this example. The other example I'm going to give is about air and oxygen. Now, oxygen welding is a technological reality for hundreds of years that those people who do welding know very well that if their oxidant is pure oxygen but not air, they can achieve higher temperatures. And as a result, they can weld metals that have higher melting points. So the reason for this is that when you do combustion in the absence of nitrogen, the energy that is taken up by nitrogen molecules to heat up nitrogen molecules is no longer there because nitrogen molecules are not there. And as a result, all the energy goes into the whatever molecules that exist as a combustion product plus whatever process that you're doing, and it is possible to achieve very high temperatures as a result. So we transfer combustion energy to a smaller number of molecules. As a result, we obtain higher temperatures. So in order to obtain oxygen from air, purify air, distillation is a common process. In order to do distillation, a separation method that is based on vapor-liquid equilibrium, we need to liquefy air first and then distill air so that we can separate nitrogen and oxygen because of their differences in their boiling points. So this is the second technology that we have. Of course, I mean, this liquid nitrogen has a new technological niche and market. So it's not just the oxygen that we need now, air liquefaction. For liquid nitrogen or pure nitrogen or other gas purification processes, we also use this. So those two examples are hopefully going to set the need and technological basis of the process that I'm going to talk about today. So we are going to start with air at room temperature or natural gas at room temperature, and we are going to bring it down to lower temperatures so that at atmospheric pressure they're going to be in their liquid state. So here on the PV diagram it may not be realistically accessible, but perhaps pH diagram can give us a better perspective on the pH diagram. let's label this as P atmospheric for the basis. All right, and this is, of course, our critical point. All right, and our isotherms and isentropes are going through this pH diagram, and we are going to use this pH diagram to understand and to design systems for liquefaction. Now, this pH diagram has isobars. So this is a constant pressure line, obviously, right? Isentropes, the constant entropy lines. All right, and with these isobars and isentropes, we will design our system. Now, we are going to, of course, start from a high volume of atmospheric pressure, room temperature gas. So first thing we have to do is to take this gas and compress it. So I will start by taking the gas and compressing it. So here is my compressor. My compressor operates adiabatically and reversibly. I do shaft work on this compressor, and there's no heat transfer. So for the adiabatic and reversible compressor, our entropy balance, and of course this process is operating at steady state. At steady state, this term disappears. The system is adiabatic and reversible. As a result, incoming stream entropy is equal to outgoing stream entropy. So I'm going to have labeled this stream as 1, this stream as 2. I have my S1, specific entropy of stream 1, is equal to specific entropy of stream 2. When I do the energy balance, this is 0 because process is at steady state. Process is adiabatic. Compressor is rigid. And around my compressor, I have my energy balance as 0 equals m dot. And of course, the steady state condition also tells me that the flow rate is constant in this process, H1 minus H2. So this is the first unit plus shaft work. First unit energy balance. Fairly straightforward. Now let's see how it looks on the pH diagram. The isotherm for the room temperature, right, should be coming from a very, it should be coming from higher than the critical point. So the isotherm, in order not to crowd the diagram, I'm just going to put dots, and the atmospheric pressure abscissa should be around here. What am I going to do? I'm going to compress this fluid adiabatically and reversibly. In other words, at constant entropy. So my constant entropy line that is going through here is going like this. Now, because I don't have much space on that end of the light board, but also because adiabatic and reversible compression is going to load a lot of energy in terms of work on my fluid. As a result, at the exit of this compression process, my fluid is going to have a higher temperature than the inlet, and I really don't want my temperatures to go that high, makes me stop at a point like this, right? At which pressure I'm going to decide to stop is a process of optimization, which I will come back after I finish the whole process of compression. Now the next thing I'm going to do is, so this is adiabatic and reversible compression. This line belongs to my compressor. The next thing I should be doing is to cool this fluid, right? Well, you might ask this question that why don't we just simply cool this fluid and condense? If you do your calculations, you will see that number one, going in that direction is going to be relatively, not relatively, very, very expensive, because we are talking about a size of 1,000 times greater. So if I'm going to start cooling a gas, I need a heat exchanger that is going to be 1,000 times larger, or on the order of, than if I'm exchanging heat to a liquid. So I cool to an appreciable temperature, but not too much, not until it comes to the two-phase domain. So this is my heat exchanger, constant pressure heat exchanger. As a result, in other words, I'm going to put a heat exchanger here, and I'm going to cool this compressor effluent stream. So this is my heat exchanger, and I removed heat. So for the heat exchanger, let me use the other color because of the space limitation, and I will write the energy balance of the heat exchanger here. So let's again finish our analysis from the general first law equation. Process is at steady state. This term is absent. There is no shaft work. Heat exchanger is rigid. So those two terms disappear, and my energy balance simplifies to 0 equals, and that, now let's label this effluent as 3, and that H2 enters, H3 leaves, plus this time Q. All right? So this is the energy balance for heat exchanger. This is the energy balance for compressor. Then I'm going to take this compressed and cold fluid, and I will find the constant entropy line that goes through this point, and I will compress it again to the next tolerable temperature, right? And then I will cool again, and this next tolerable temperature is still not bringing me slightly above the critical point, and I really want to come slightly above the critical point. So I will cool this one again. Let me use this line as my guide. I will compress meaning that I have 2 more units of compression and cooling. I'm not going to write the energy balance anymore. Nothing is new. The energy balance is the same. The energy balance is the same. This is going to be valid for this compressor also, with the indices changed. And this is going to be valid for this exchanger also, with the indices changed. So it will be, instead of 2 minus 3, it will be 4 minus 5. All right, I'm at step 5. This was my second compressor, second heat exchanger. Now I need another compressor. Let me just change the direction so that I will have space. This is 6. Now what am I going to do is the following. I'm going to cool this as much as I can. And this temperature is also an economical decision. It's not just a decision relying on the physical properties of the fluids, but also process economics has to come into play. So here I'm at this temperature, T6. Let me label my points. 1, 2, 3, 4, 1, 2, 3, 4. My 5th point is here. This is point 6. And now I'm going to come to point 7 after a heat exchanger. And then what I will do is I will use a throttle valve and do isenthalpic expansion. All right, constant enthalpy. So after the heat exchanger, I have a throttle valve. This is 7. This is 8. As you can see at point 8, we have a mixture of vapor and liquid. So we have to separate vapor and liquid. So we just take this fluid into what we call a flush drum. So let me do a little bit of so that we have liquid and vapor separated, and this is our desired product. All right. What I draw here is the simple liquefaction process. Simple liquefaction process. I just take air, compress, cool, compress, cool, compress, cool. Constant enthalpy throttling. So let's write the energy balance for the throttle. Compressor, heat exchanger, so let's write throttle here. Around the throttle valve, again, it's operating at steady state. There's no heat exchange, there's no time for heat exchange. There's no shaft work, there's no surface boundary movement work. And the energy balance is 0 equals m dot H7 minus H8. All right? So the throttle process is constant enthalpy. From here, we immediately deduce that H7 and H8 are equal. Hence, we have a vertical line going down in our pH diagram. And now we have a liquid and vapor mixture. We have to separate. Let me call this stream 9. Let me call this stream 10. And this is the simple liquefaction process. Now let's discuss the optimization. Now, here in the compressor, the first stage is the most demanding one because we are using the largest volume, the high temperature, largest volume. So when we both start from a very large volume and we also start from a high temperature fluid. As a result, as we compress, the temperature increases, all right? And this temperature increase has to be checked, has to be controlled. The material of the construction, because those compressors need lubrication fluids, the resistance of those lubrication fluids to those temperatures should be taken into consideration. So you have a technological limitation to how high the temperature should be. Number one. Number two, we shouldn't have very high volumes to heat exchange, right? Our heat exchangers should be designed such that, or the final pressures should be chosen such that we will have a reasonable size heat exchanger here. So we're going to have not too much volumes. Then the second stage, then the third stage, and so on and so forth. And of course, this final position, how far we can cool this fluid depends actually on mostly on the boiling point of this fluid at atmospheric pressure, of this liquid at atmospheric pressure. All right, we really would like to make use of this system and its energies to exchange heat. So it is a very common practice of using this stream to exchange heat here, sometimes here and here also. But now this simple liquefaction process is inefficient in the sense that part of the product is being discarded as vapor. After, of course, we have done the heat exchange, right? So now, the better solution is to recycle. And the recycled process is going to be called the Linde liquefaction process. Linde process of liquefaction. In this Linde process, our flow chart has similar characteristics. We have compressors, we have coolers or heat exchangers, let us go again with the three-stage compression and cooling. Then we will do the throttling. Again, the same process. Then we will do the separation. We'll take the liquid in this direction. And what we will do is to take the vapor, perhaps do this heat exchange for us. Perhaps do this heat exchange for us. And then being a cold fluid, go and combine with the feed. So here at the point of mixing, we have a low temperature and a high temperature fluid mixing. We have a little bit of medium temperature fluid. So instead of starting all the way up here, we now made good use of the coldness of the vapor, which is in equilibrium with the liquid that we wish to obtain from this process. So we start from a lower temperature than a simple process, right? Now, this heat exchange cascade and feeding a cold fluid is going to change our game a little bit more. How so? Now, because I have a fluid that is going to be warmed by the latest point in the process diagram, will give me a temperature that may not be as low as I wish. So how far I'm going to be able to come here is also going to be determined by the temperatures. So these are our design parameters. My design parameters are the pressure of the second stage, temperature of the third stage, pressure of the fourth stage, temperature of the fifth stage, and so on and so forth. And by adjusting those, what will be the most optimum temperature, what would be the most optimum pressure in stage 2, stage 3, will be decided after numerous calculations. Now, when I look at the Linde liquefaction process as a black box unit of what comes in and what goes out, I see the following. Gas comes in, liquid goes out, we have significant amount of shaft work into this system, and we removed considerable amount of heat. So, with the liquefaction process now, we can start making calculations. But in order to make calculations, we need a pressure enthalpy diagram. Pressure enthalpy diagram for nitrogen, for air, for methane are available. So for many other gases are also available, but in our textbook these are available. So we are going to work on nitrogen liquefaction, methane liquefaction, methane for natural gas, for compressed natural gas or liquefied natural gas, and air liquefaction process.